All right, so why do we need to understand the four fundamental forces and what happens to them at higher and higher energy when dealing with the very early universe? Well, remember, the universe has been expanding. As things expand, they tend to cool. So if we go backwards in time, then everything had to get closer together. The entire universe has to shrink, which means it also has to heat up. So if we want to understand the very, very early universe, we have to understand what happened when things were very, very hot. And so, as we go farther and farther back, we have to deal with these ideas of dealing at higher and higher temperature. If we go back to the very, very beginning, the instant of the Big Bang, okay, so the instant of the Big Bang is when the universe begins to expand. What happens before the Big Bang, we don't know. Why it happened, we don't know. We just know that it must have happened. So this instant of the Big Bang is where the universe suddenly began to expand. Now, one thing we know is that it had to be incredibly, incredibly hot. Okay, so for the first 10 to the negative 43 seconds, the universe was over 10 to the 32 Kelvin. In other words, it was super, super crazy hot. It was so incredibly hot that to be able to describe anything that happened during this time, we have to have a theory of everything. And if you remember, we don't have a theory of everything. We don't even know what a theory of everything will even look like. So we have no idea what's actually going on here. Okay? Our ideas of what's happening during this very earliest time, we don't know. Okay? This very earliest time is known as the Planck era, and we don't know what's happening during the Planck era. That's not entirely true. We know one thing. We know that the universe is expanding, and it is also cooling. Okay, so the universe expands and cools. So that at 10 to the negative 43 seconds, it cools off enough that we go from a theory of everything to just needing a grand unified theory. Specifically, gravity freezes out. What we mean by freezes out is that gravity becomes its own thing. It becomes distinct from the other forces, which are still unified. Okay, so at 10 to the negative 43 seconds, gravity freezes out, and this then begins what we refer to as the gut era. So to describe what's happening during the universe at this stage, we have to have a grand unified theory. And if you remember, we don't have a grand unified theory. We do have some things that different approaches of grand unified theories actually agree on. So we kind of get a vague hint and possibility of what the universe was actually like during this time, but nothing is yet set in stone. But again, we do know that the universe continued to expand and cool, so that at 10 to the negative 35 seconds and 10 to the 27 Kelvin, it cooled off enough for the strong nuclear force to freeze out, for the strong nuclear force to become distinct. Now, when this happens, when the strong nuclear force freezes out, it actually triggers an energy level shift within the rest of the universe. Okay, so if you remember back talking about atoms, electrons and atoms can be at different levels. Okay, so we have what we call energy levels. And if it has a high energy, it can drop down to a lower energy by releasing that energy, usually as light. Well, the entire universe kind of went through this. It was stuck at kind of a high energy level, and then it transitioned down to a lower energy level, releasing that energy. Now, for a very, very brief amount of time, that release of energy actually went into the expansion rate of the universe, so that the universe itself began to expand faster than it had previously. Specifically, based on what we can tell, during this period, the universe expanded faster than the speed of light, which I realize sounds crazy because we've stated before nothing can travel from light faster than light. But the key is that it is space doing it, not matter doing it. Objects within the universe can't go faster than light, but the universe itself can. I know, it's weird, it's a whole thing. Just nod your head, smile, and accept it. All right, so after inflation ended, the universe again continued to expand and cool, so that at 10 to the negative 12 seconds and 10 to the 15 Kelvin, we finally have all four forces freeze out. Okay, so we go from the Planck era, where everything is unified, to the gut era, where Gravity is separate from the other three forces. Then we have the electroweak era, where we have gravity, the strong force, and the electroweak force. And then starting at 10 to the negative 12 seconds, all four forces have now separated, have frozen out. So all of them are clear and distinct and behaving in ways that we can actually understand, or at least experiment and find out about. All right, here's our next question. E equals mc squared shows mass can be turned into energy, and energy can be turned into mass. Go ahead and think about it, and we'll discuss it in just a little bit. All right, so the correct answer is true. E equals mc squared shows that mass and energy are interchangeable. Okay, so previously we saw it go the other direction, where matter is being turned into energy. This is what occurs during fusion in stars. Okay, as hydrogen is fused into helium, we lose a little bit of mass, which is actually released as energy. Okay, however, at this stage of the universe, we have the other process occurring. There is so much excess energy of the universe that energy is actually being turned into matter. This is what is happening during what we refer to as the particle era. Okay, so during this process, we have pair production. What happens during pair production is we have two very high energy gamma ray photons collide together and create a pair of particles. We get a matter particle and its antimatter equivalent. Okay, so I think we talked about antimatter previously, but in case we didn't, antimatter you can kind of think of it as a mirror of regular matter. Okay, so for every matter particle, there is its antimatter equivalent. And the antimatter equivalent has opposite charge and opposite other fundamental quantities that we're not getting into. Okay, so as an example, we can take the electron. Okay, the electron is matter, and the electron has a negative charge. So the antimatter equivalent of the electron will have the same amount of mass as the electron, but instead of being negatively charged, it is in fact positively charged. Okay, so this is what we refer to as a positron, sometimes also referred to as an anti-electron. Okay, so in pair production, we always create the matter particle and its antimatter equivalent. That is why it is a pair. Now, when matter and antimatter get together, they annihilate. They go from being mass back into being pure energy. Okay, so this is the process of annihilation. Now, at the very beginning of the particle era, okay, when it was still really, really super crazy hot, we had both processes happening in equilibrium. For every pair of particles that were created, a pair of particles were annihilated. However, over time, as the universe expands, the temperature also decreases, which means we have less and less energy. So to start out with, we can create all particles, high mass, middle mass, low mass, everything, we can do it. But over time, we can no longer make the high mass particles. There's not enough energy to create high mass particles. But we can still do middle and low mass. Then as the universe expands and temperature drops, then we can no longer make the middle mass particles, but we can still do the low mass until at the end of the particle era, everything finally cools off enough that now we can't even make the low mass particles anymore. Now, during this process of pair production, we stated that for every particle that is produced, we also create an antiparticle. Okay, now what this means is over the course of the entire universe, every particle should have found its antiparticle, which means that there shouldn't be anything in the universe. Everything should have annihilated. And yet, we know that's not the case. There's still clearly matter within the universe. Okay, so what this means is something had to happen. Now, we don't understand exactly what. This is still an ongoing question. But it appears that for every 1 billion antiparticles that were created, 1,000,000,001 matter particles were created. Okay, so those extra billions annihilated each other and were left in that 1 billionth remainder of matter within our universe. Now, again, we don't know exactly why or how this happened. It's an ongoing question, but there are certain particle physics experiments that are kind of hinting at how this could happen. But again, we don't know for certain.